Hi, in this video we're going to explore the gradient. So first I will explain what is a gradient, and then I will explain scalar functions and vector fields because I believe they are related to gradient. And then I will show how gradient turns a scalar function into a vector field. And then I will show an example of what is the use of gradient. So let's begin. So let's say you want to find how much your function changes. That would be basically what is your rate of change in x direction and how much you moved in x. And similarly, what is our rate of change in y and how much we move in y. So then you can make this expression into this format. This is simply just a dot product, and if you just do the dot product, this being multiplied by this plus this being multiplied by that one, will just simply give you that. So let's say you went infinitely small, that will be just the differential. But here is one important note, because our function here, I will get into this in more detail, this is just the introduction. Because we have like x and y at the same time, we must do the partial derivative. So this is like similar to derivative, but the partial version of it. And so then we have this left over. This is our gradient, and this is the direction we move. But right now I'm not going to focus on this. I will just show the gradient first. But before all of this, we must first understand these type of functions, and then how they will turn into this vector field. So let's begin with functions. This would be an example. So we have our function. This is our input, and we get the output here. Similarly, we might have a different function, which would be maybe this one. But now we have two inputs and our one output. And we might have three functions. Actually, let me give you another example here too. We might have another function x, y. So we have two variables, two inputs, two variables, and still one output. And moreover, we might have three variables. So now it's kind of 4D. This is 3D, this is 4D. I will get into this. Three inputs, one output. Maybe another function. So what would happen if you, for example, say y equals f of x, and maybe z equals f of x and y. Maybe a t equals f of x, y, z. So now I will show you the visual representation of what is going on here. So let's start with a simple one here. Maybe I can make it bigger. Oh my god, what did I do? So this is just a parabola, right? We just have a horizontal shift, in like two horizontal shifting to the left. It's kind of looking bad, but I think you get the idea. So what does this represent is that when your x is -2, your y, your function output is 0, which makes the y 0. Your y height is 0. And when maybe your x is now 0, your y becomes 4. Gives you somewhere here, let's say. When your x is here, your y is here. So we have input, our input is x, and then our output is y. And when we combine the coordinate like this, our x input and our output, the function, this is our y, we get a point. This is a point. And when we plot infinitely many of these, we get this shape, right? And so similarly, it's the same idea for these ones as well. Now we go into 3 dimensions. But I think it would be better to actually show you in Desmos than actually me drawing it. So let's move to Desmos. So now we are looking at z equals x squared plus y squared. Ignore the ones below, I will show them later to you. That's about level curves. So we get something like this, right? So when our x is 0 and y is 0, we get our z 0. It's right here. As they get bigger, for example, at 1, 1, our x is 1, our y is 1, our z is 2. And then at, for example, at 2, x equals 2 and y equals 2, 2 squared plus 2 squared, that's 8. So our z is now 8. And the relation here makes it that the shape looks like a parabola, but it's rotating around itself. And it's like a surface. It's not like a volume, but like a surface. So it's like as we move on the xy plane, which is here, as we move on this xy plane, our coordinate, for example, if it's here, we move to maybe here in z. And if we plot all of them, infinitely many number of x and y, and then we will get this shape. And similarly for our other function, z equals x and y, we will get this shape. And if we plot all of these x and y values, like if we have, for example, one point here, our x is maybe let's say at 2, and our y is, that's not 2, 2 is probably here, it's something else, 1.5 maybe, and our x is 2, we will get a point somewhere here. Our z will be somewhere here. And as we plot all of this, we get this shape, this surface. So now let's say you want to draw this in 2D. You want to draw this 3D function or 3D looking function into a 2D version. How you can do it? So that would be a level curve. And simply you will just make a XY plane now, and you will turn the shape into how it would look if z was a constant number, like let's say 1, or maybe z is 2. I cannot make a circle. Yeah, I think you get the point. Z equals 2, for example, let's say, or z equals 3, and so on. And this would be a level curve for this function here, the one on the left, this one. Actually, I can show this better in Desmos, but also let me do the level curve for this one as well. So if we look like something like this in level curves, so let's go to Desmos. I think that would be much more helpful. So our initial function looking like this, if we make the z into a constant 0, we have nothing, because 0, 0, 0, that's just a dot at the origin and we can't see it. But let's say z is equal 1 now, we get a circle. So x squared plus y squared equals 1 is just a circle. That's the equation of circle with a radius of 1. At 2 it looks like something like this, at 3 it looks like something like that, and so on. So what this actually represents, that when the x and y value is somewhere here, our z is 2, right there. So this is a level curve. These, all of them are level curve, and we have infinitely many of them. So at this location, exact this location, our z equals 1, the green one. And then if we look, we go up. I mean, we can't see it right now, but yeah, can you see it? Actually, this way maybe I can show it easier. This is z equal 1. So if we now go to side, yeah, we have 0.8 here, it's probably 1 here. So we are at z equals 1 level. And if I go up and zoom out, exactly here, our z is 2. At exactly here, this level, our z is 3. If you zoom out more, at exactly this level, our z is 4. And exactly here, our z is 5. Can you imagine this now? Like, this was what I meant when I said that on this xy plane, when our values are, for example, here or there, it plots up. Like, we plot the z location, and we get this, right? So basically, this is how the plane looks when the z is constant. So now this is a level curve. So this way we were able to make a 3D function into a 2D looking thing with level curves, and we can plot infinitely many of these, and we can make it look like a 3D function into 2D. And similarly for the other one, this one right here, if I open all of the other ones, you will see that, maybe I will close the main function, at z equals 0 level, our either x or y is 0, that's why we get this line. And at z equals 1 level, we get this curve, this level curve, and so on. These ones go to infinity. And if I open the main function, you will see it actually. And maybe I can actually add another one and say when z equals -3 maybe. As you can see, when z is -3, we are somewhere down here, right? So we get it on this side. I hope that makes more sense this way. And so this is a level curve. And yeah, basically this is the idea behind it. So now let's move to this one. So you see that this is just a surface, and this was just a curve, and this is how a surface looks in 2D. Now here we got something more complicated. Now we got a 4D shape. So this was 3D, now we went to 4D. So now we have surfaces, and they're just expanding outward. I will show that in Desmos again. We got this function, right? Our function is x squared plus y squared plus z squared. And as our t change, we can see that this is now like a volume. This is not like a surface, but assuming that t is everywhere, like t is all numbers, just the rational ones of course, we get this volume like everywhere. So basically this has no real meaning by itself this way, because neither our x, y or z is constrained anywhere. So it could be anything, and this causes a problem because if you think about it, this is just like a anywhere. This is like a function that could be anywhere simply. So this has no real meaning. So let's give t a number. Let's say t equals 0. We see nothing because that's just a dot in the origin. So let's say it's 1. We get a sphere. So if you think about it, x squared plus y squared equals z was a circle, kind of. But now, because we have also the z squared adding it to this, we now kind of move in all 3 dimensions and it becomes like a sphere, maybe a circle rotating around itself. And now we get this. And if we zoom in, we will see that actually this is a surface. This is not like a volume anymore. And if I take this and say maybe at 2, we get a bigger sphere. At 3, we get even a bigger one. At 10, you see it's like expanding out. So now this is a new idea. Now this is a level surface. So do you remember like how previously we made a 3D surface, a function, into a 2D level curve? Now we are basically making a 4D function into a 3D surface, a level surface, and each one of them is a level. Now at this level, our t equals 10, this purple level. The other ones, our t was 3, our t was 2, our t was 1. So now this is a level surface. And similarly, for the t equals xyz function, this has no real meaning because it's 4D, it's everywhere. The xyz has no real constraint, so we in a 3D world here, we can't see 4D. That's why we cannot basically imagine this function, because this is basically 4D. And before, like in the previous example that I showed here, we made this 3D surface into a 2D, and we can easily imagine this, right? Because we can imagine 2D and 3D. But because now this is like a 4D thing, we cannot simply just understand it. So before we made a 3D into 2D level curve, now we will simply make it into a 3D surface. So our first level curve at t, for example, equals 3 is looking like this. And just don't try to comprehend how we get here. This is kind of a hard thing to maybe imagine, and I understand that. So this is just, I'm explaining the idea behind it, so just bear with me. And at t equals 5, we have another level surface. T equals 7, another one, and another one, and another one. And we get this a fabric that is getting more and more. Do you see it? This is simply how we went from 4D into a 3D shape, and each one of these colorful sheets are basically a level surface. And actually maybe I can expand them out. You can see the difference between them easier. Let's make this one 20. So we now hopefully can understand level surfaces. And I don't have the drawing of the 4D function here because it's kind of hard to comprehend, and I don't think there's any reason to understand it, because if we can see the level surface, we can just simply understand the function. So now I explained all of this. These are all scalar functions. And I will get into a moment, in a moment I will explain why I call them scalar functions and why they are actually scalar functions. Before that, I have to first explain vectors, I think. So let's now explain vector. What is a vector? And I will relate that into a vector field. So a vector has a direction and a size. So let's give you an example. In the xy plane, let's say from origin 0 to here, we have a vector, and this is 3 and this is 3. So our vector is pointing to 3, 3. So it has a direction and size. And for example, maybe another vector pointing this way. This is 2, this is -3, and maybe this vector g is -3 to 2. So this thing we see here and here, this is how much, or what is our direction in x, and this is our direction in y. So this is just I, j, and k for the third dimension z, but we don't have it in this example. So before, we had a point in space, and we were showing it with this notation. Let's say point of 3 and -4. Or maybe you can also say it in like 3D and say maybe like z is 5. So this is a point, and this is scalar. It has no size. This is just a point in space and has no direction. I mean, you could imagine this as like a something pointing like in three dimension. You can imagine that something is pointing to this point and say this is maybe like a vector, but that's actually not like a point, like a vector, but like a point in space. But now in vector, a vector in space, we have this notation. So now we don't have the bracket like this, but a bracket like that one is maybe like this. You have both size and direction. So our size would be square root of 3 squared plus minus 4 square. Basically the Pythagorean theorem. I won't get into too much detail. I'm assuming this is known, but just to like show the idea. Equals 5. And our direction is also shown on the vector, but if you just want a pure direction, a unit vector direction with size 1, you will divide your vector by its magnitude, size, and we have this. So our direction, only the direction, is this. So you might ask, what about the location? It's unknown. So this vector is basically could be anywhere. So we see that it's pointing a little bit to the right and a little bit down. It should be like this. This vector could be anywhere. We don't have any location for this vector. So you could think it as like everywhere. Could be anywhere. That's why I'm drawing it anywhere right now. And yeah. So what if now we have a function that specifies both the vector and its location? Then now we have a vector field. So now we moved on from this to that. And this is just the example, but now your vector has a location, 2 inputs. And as you can see, our vector here is depending. Now, like the vector doesn't have a constant number like this one. This had a constant number, but we no longer have a constant number, but they are changing, they are variables. So as the location change, our vector change as well. So let's actually draw this and plot this actually to see like how this is looking. So at 1 1, at the point 1 1, our vector is just simply 1 1. So let's go here. Let's say this is 1 and this is 1. At this location our vector is 1 1. So we go, let's say this is 2, this is 2, we go 1 to the right and 1 go up, and if we add them together, vector addition, we can add them tip to point end to end, get something like this. Let me delete those ones. And what about maybe at minus 1 1? Our vector is just this. So we go 1 left and 1 up. When I add them together, we'll get something like that. And so far, so on. This will look like that one. And let me maybe actually show this one too. So we go 1 to the left because this is minus 1, and we go 1 down because this is minus 1 as well. And if you add them together, I mean, it's not to the scale, but I guess you get the point. And it's so on and so forth. We get this, right? And so on. If we plot this more and more, infinitely many points, we get this. More and more. But I want to point out something to you. The size is changing, as you can see. So let me plot a point at 2 2. So now our vector is 2 2. So at 2, let me erase this vector, maybe make it a little bit smaller. At 2 2, our vector goes 2 to the right. Maybe this is like, here's 4 maybe, and here is 4, and goes 2 up. Actually, maybe it's higher, somewhere here. So the vector is now quite larger, actually, as you can see. So this was one of the mistakes that I did before. A vector field the vectors are not same all the time. They are changing in size. So before here, our vector size was root 2. Now it's root 4. Actually, not root 4, root 8. 2 square, yeah. So it's changing, the size is changing. And this vector field right here is actually diverging. But this is a concept for another video. Right now, I don't think I can explain that one as well. It's going to get so much longer. And similarly, you can also have a 3D vector field. And maybe for this one, x, y, z, I will repeat again, 3 inputs, and these are the location of vector, and our vector is dependent on the location. So as location change, vector changes. Let's go show this in Desmos. Let's not look at the function, but this is the idea. Do you see that they're all pointing away from the origin? It looks a little bit bad like in 3D, but if I look from above, you can see it's pointing to the right. If I look from this side, it's pointing like that way. Pretty similar to what I draw, but in 3D. Other direction, it looks like this, and they're pointing all away. And you can actually, if I zoom out, you can see that, see this vector right here, it's quite larger than the vector right here. Their size is changing. So size changes as well, not just the direction of the vector. So now hopefully we have a better understanding of both the vector field and the scalar functions. So now we can begin with the idea of gradient. I will repeat again because we learn with repetitions. So this was our rate of change. Rate of change when we are going in x direction. And this is how much we actually moved in x. And this is our rate of change when we are moving along y. And this is how much we actually moved in y. And in result, it will give us how much we are changing the function. And this function, let's not get confused by this function, but this was simply either y or function was z or function was t, as we saw before. So our function, I'm not specific, like in that specific example I showed, it's probably this one because it had both x and y over there. You could have also a gradient in the fourth dimension, which I will get into it as well, but so yeah, maybe this is not the right example, but this function is actually the f of x and y, which was equaling z in this example. So which is also changing z. So how much the height is changing, we are basically doing. And if we move forward, this was just a dot product. And if we went infinitely small, we move into differential territory, and this becomes a partial derivative. And I will explain that in a second as well. So one thing you might notice is that this is a vector field. I will get into that more, but yeah, let's look at partial derivatives. So let's say we had the function we had before, x and y equaling x and y. Our partial derivative of x will just simply say that we treat y as a constant. And then we have x is becoming 1 and y stays as is. And we have this. and partial derivative of y is just simply we treat x as a constant and we take the derivative of y. So then we are left with this. Moving on, then this transforms into this notation. This is our vector r, but because we are taking the differential, becomes dr, and we have our partial derivative of x and y, and this becomes grad f. At least this is what we call it basically. So now I'm not gonna focus on the dr part, we're just gonna focus on the grad f. So what is this? And what happens when we take gradient of a function? So our example that we had before, f of x and y was equaling x squared plus y squared. And we saw that it was looking something like, so let's take grad f, which is also same as grad z, is the partial derivative of f to x and y. So we will have 2x plus 0 because we treat y as a constant, and constants in derivative they go away when they are alone, and our 2x squared becomes 2x. And similarly for the other one, we have this, which is just 2x and 2y. So you might notice that, yeah, this is a vector field. Actually, maybe I will do it this way. This is a vector field. And because maybe I don't have this xy here, you get confused, but like I said, this is our location and our vectors depend on the location. So our vectors change as the location changes. So let's go and actually see how this vector field looks like. And you might also notice that this is a 2D vector field. This is not 3D. We had like a 3D function here. It looks like 3D and it's like a surface, but our vector field is in 2D. So how is that going to work out? That's why I was talking about level curves, because our vector field or gradient is existing on a plane, on level curves. And let's go see them actually. So I went to 2D Desmos, but this was our function, right? So I'm just moving it into x and y. And looking at it here, we can see that our level curves, which are these ones, we have one at 50, one at 30, one at 9, and our partial derivative. Let's, like, I know this kind of looks confusing here, but so this is our partial derivative in x, and this is our partial derivative in y. So I basically just did the same thing, just the notation is a little bit different here. And as you can see, the vector field is pointing from a lower level curve to a higher level curve. So right here we have our z equaling 1, and then our vectors are pointing away. I mean, it's not a very dense vector field, because if I put more vectors here, it's just going to look so messy. That's why you can't see all of them, but as you can see, they're pointing away from lower level surfaces into higher level surfaces. And so our vector field is kind of perpendicular to the level curves, and it goes from lower to higher. So I just want to write down two important things. So yeah, vector field of a 3D surface is in 2D plane. Vector field gradient is perpendicular to level curves, and gradient or vector field points from lower level curve to a higher level curve. I feel like this video is getting a little bit long, so I'm gonna speed up. And for our other example, z equals f of x and y was equaling xy. Gradient equals and we have this. And moving to Desmos, we again have the similar thing here. We have our level curves here. We also have level curves here too. But just looking at the positive z values of level curve, you can see that the gradient is pointing from a lower level curve to a higher level curve, and it goes so on and so on. Paying a close attention to the size, we can see that the size is quite different here as well, because I think the curves are going up steeper and steeper. So, I mean, this one is 20 and this one is 30, so this one is 30 and this one is 20, but still, like, getting to this point, there is a more steep location at that point, and you can also see it in the function itself. Because it's getting steeper here, our length of gradient vector at that point is getting longer. And if we imagine it, gradient is pointing like this. It's not like pointing up, but it's like in a plane. So it's like this. I hope this was better to understand this way. And now let's look at the other gradients. And our gradient f, which is also same as gradient t, because they're equal to each other. And I'm not writing the whole thing, that's why you might also get confused, but now we're just simply adding the third dimension. So now, treating for x, we are treating y and z constant, so they become 0, and we have just x left. And for the y, similarly, we're treating x and z constants, and for z we are treating x and y constants. So we have this vector field. And let's look at it in 3D. And this is how it looks in 3D. So let's actually, it's gonna get a little bit yeah, messy, but as you can see, this is one level surface, the idea we were talking about. And at t equals 10, we have another level surface. At t equals 20, we have another level surface. Actually, we have infinitely many of them, but I'm just putting 3 of them. And as you can see, the vector field is pointing from a lower level surface to a higher level surface in 3 dimensions. So did you notice that now vector field of a 4D function is now a 3D vector space? Before we went from, when we had a 3D function, a surface, our vector field became 2D. But now because we had a 4D function, now our vector field is 3D. And if I put the other one, I hope it's easier to understand this way. And it's diverging, the vector field is diverging. But this is another idea for later. And also if you pay close attention, you can see that the vector field is the vectors are getting bigger here as we go outside, and inside they are smaller, they are tiny, and they get bigger as we get farther away from origin. And now let's quickly look at our other function. This one was t equals g. Our function could be any letter you want, except maybe x, y, z. Let's not reuse our variables. So grad g, which is also grad t, equals partial derivative of x, partial derivative of y, and z. And treating the other ones as constants, x becomes 1, the other ones stay, y becomes 1, the other ones stay same, and z becomes 1, the other ones stay. And going back to the Desmos, we had this function, right? Before we were seeing, we had level surfaces, f4D functions, level surfaces, and now our gradient field, our vector field, looks like this. It looks a little bit messy, but maybe we should look at individual parts. Let's look at only here. So as you can see, pointing from a lower level surface to a higher level surface, and this is pointing to this one. And yeah, as you can see, the vector field, the gradient, is going from lower surface level to a higher surface level. And you might ask, what about this empty space here? So this is actually a proof that this is 4D. So before we had negative z values, right? But negative z was like at this below, right? Because we have z here, and negative z would be here, somewhere here. But now, because no longer z is the function equaling to the function, but z is the variable, if I go and make this negative 10, becomes here. And if I make all of them actually negative, you will see that they switched location. So this is 4D, but we are seeing the level surfaces at some constant numbers. And here actually you can see that you might be like, why the vector field is pointing downward now? I thought it was going from lower to higher, but no. Here we have t equaling -1, but here we have t equaling -10. So our vector field is pointing from lower level surface to a higher level surface, and this is lower. And we have here t equaling -20. It's pointing from here to the other one, as you can see. And I could add the other ones back, and you will see that this is how it looks in 4D if you have almost all of the Z levels. It looks confusing, I know, but I hope this is giving you more idea on how the vector field, that actually the gradient, I should probably stop using the vector field word and start using gradient. Our gradient is perpendicular to the surface levels. One common thing that you can see, as you can see, it's all of them are perpendicular to the surface level, and they are going from a lower surface level to a higher surface level. So let's write out the common pattern we saw. Gradient is perpendicular to level surfaces, and gradient points from lower surface level to a higher surface level. So now let's move to the meaning of this. Directional derivatives. So let me put a question up here. Let's say you are at the point 2, 4, and you're moving in this direction 1, 2. How fast are you rising in Z height along the path? So we are in kind of like 3D, right? So if you are moving in this path, how fast are we rising in Z? And this is our function, the function we had before. Let me actually put a picture of it. Our function was like this. So let's write down what we knew before, because this is kind of different. We said our change in f was change in our rate of change times how much we actually moved plus rate of change divided by how much we actually moved, and we could write this as a dot product and if you go infinitely small, we move into differential and partial derivative territory. And then this was equal to grad f times dr. So here it's not asking how much we moved in z, but how fast we are rising. So this is kind of different. So now this, we have to divide everything by ds. So you might ask, what is ds? Let's talk about s first. S is the arc length. So let's say you have a path r. This is a vector function. I was talking about vector functions in the previous video, but briefly talking about it, we have this vector function r of t. If we think that this is in 2D, let's say if we look into like something like this, our arc length would be just the length of this whole curve right here. If you add up all of this with some integration methods, this would be the length. So, but what is ds? ds is the tiniest bit of this length, kind of. So when we divide df by ds, we are saying how much f is changing per unit change of arc length. So we divided df by ds. So then this means that we have to divide this whole thing by ds. So df ds equals grad f times dr divided by ds. But now you have a choice. You can either divide grad by ds, gradient by ds, or dr by ds. If you divide gradient by ds, this is gonna make it complicated and not much meaning. So I actually never tried it, but don't try it. So then we are left with the only other option, grad f times dr ds. So you might ask, what is dr ds? So this is not written all the way, but this r is actually a vector function, another different type of function that, yeah, I said that I talked in the previous video. We might get technical and say this dr ds is actually dr divided by dt by the chain rule, and ds divided by dt, which is velocity divided by velocity's magnitude, speed, which equals into a unit vector, tangential unit vector to the path rt. But we don't need that idea right now. We are given that information in the question. We are saying we are moving in this direction at the instant when we are here. So we don't need any of this. So if our path was something like this, at this instant, the question is telling us that we are moving this way. And this equation also finds which way we are moving at this instant. We can find it too. But we don't have this. We don't have the position. We don't have the path, or of we don't have the vector function rt. So we use the information given by the question, which is this. We go and transform this 1, 2 into a unit vector. So we divide it by its magnitude, which becomes 1, 2 divided by root 5. So now this is our unit vector direction that we are going at 2, 4, which is equal to this thing, to not this thing but this. So we can essentially come and write the equation we had before, df ds equaling grad f times dr ds, into this. So this is our now unit vector, and if we dot product the gradient vector at 2, 4 location, we get an answer. It's now, I think this is going to confuse people, so let's go in Desmos. So this is what we had before, right? So we are gonna go at 2, 4, right? Let's go to 2, 4. Where is 2, 4? So at 2, 4, we are at level curve z equals 20. And we are standing right here. Our gradient is pointing this way. And we are moving in direction 1, 2. So 1 here and 2 up. Let's draw this in blue. So we are moving in this direction. But since we don't care about the length of it, we will make it into a unit vector we had before, and we dot product them. So because gradient was both the direction and the size rate to the fastest path going from a lower level curve to a higher level curve, it is basically telling us at what rate our z is increasing toward the best direction it could go. So by doing a dot product between the grad f and our u, unit vector u, we can find out the rate at which the z is increasing on our specific path at that instant. So let's go to our actual function here. At z equals 20, we are somewhere here, right? And it's 2, 4 here. You have to zoom out quite a lot. And let's find it. I think this is the perfect height. And so at z equals 20, we are somewhere here, right? We are somewhere here. In this level curve, we are in this top region. And at 2, 4, we are right here. So it's here. So grad f was pointing this way in 2D in this level curve, and if we go this direction, u, and dot product the grad f, by u, we will get the rate at which z height will increase on that path. So let's go to the question and now find out what is this? So first of all, we have to find the grad f at 2, 4, because as you can see, our grad f, but this is only for the grad at this specific location at z equals 20 level curve. So we go and first find the grad f. It was partial derivative of x and partial derivative of y. Our function was that, and we find this. This is our vector field. Gradient. So now we go, and actually if I draw it the full version, as you can remember before, we had this, right? So our vector had a location. So this is similar to that idea. We will put the location in here. We were at location 2, 4, as the question is telling us, which equals 2, 2, and 2, 4. So this is our specific vector at that location. And we found u, unit vector u, and it was this one. So let's go and do dot product between them, as shown here. So our df, ds, let's zoom in a little bit, equals 4, 8 times 1 divided by root 5 and 2 divided by root 5. This is same as this one, so I'm just writing them together. And let's do the dot product. So 4 times 1 divided by root 5 plus 8 times 2 divided by root 5 equals 4 divided by root 5 plus 16 divided by root 5, and we got this. So this is our answer. We move 20 divided by root 5 up per small per unit of change on the path. So this is just a number, 0.944 meter. So a physical example would be 8.944 meter height per meter path. How much you rise if you go, this much on the path. And I wanted to do one more example, but I've been recording for 2.5 hours, and yeah, and also I don't think at this point anyone wants more. So let's go to the top and do a quick look at what we did. So we first introduced the idea of gradient, then I explained scalar functions, how all the inputs go, and with one output we can have many points in space, and they will add up and make a curve or a surface or a 4D shape, which I cannot draw. But then we introduced the idea of level surfaces and level curves here, and we saw examples with those and how the functions look. And using those ideas, we went and introduced what's a vector, and the difference between a vector and a scalar function, then we saw that a vector doesn't have a location, it could be anywhere. So we introduced a vector field idea, that now the vector has a location and the location changes the vector. And then I showed you a simple vector field example. Then we moved into a 3D vector field with a simple example as well. And how the location was changing and everything. And we moved back to gradient again. And I showed you how this was actually, now you can actually see that this is a vector field. And we tried to understand how a scalar function went into a vector field. And the next step, I showed you that. So taking the partial derivative in x and partial derivative in y and putting them into something like this made it into a vector field. And how this vector field was perpendicular to level curves and level surfaces, which I will show next. And how the vector field, the gradient was pointing from a lower level curve to a higher level curve. Then we went into a 3D version of gradient and how a 4D function then was shown in 3D and how the gradient turned to be a 3D vector field. Again, it was the same idea. The gradient was perpendicular to level surfaces and it was pointing from a lower level surface to a higher level surface. Then we talked about the applications of this. Directional derivatives. And how, if you are at a specific location and you are going in a specific path, you could calculate how efficient this path is actually. So if you want to go up on a curve as fast as possible, you go in direction of gradient is pointing you. If gradient says go this way, then go that way to go fastest up. But since now we are going in this specific direction, let's say we are going this way, now this is gonna drop the efficiency of this climbing. And then we can see how the rate is affected from that by doing the dot product between this path of unit vector and the gradient at that location. And we also saw the RDS, but we didn't need this idea yet. The direction is given to us in the question. And yeah, thank you for watching. I hope the video was helpful. It is probably a little bit long, but the concept is quite challenging, I think, and I hope I was able to explain it good. Thank you for watching. Sound calibration done. I hope I'm not making any math lords angry. This is getting into one of those territories that my knowledge is kind of not enough. Let's actually ask GPT, maybe it knows. Like, I'm talking like I'm explaining to myself. Oh no, okay, scan.